Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help us out over here. And it also helps us reach others in need of assistance with these topics. So what we're going to be going over today is differential equations, talking about separation of variables and how to solve using separation of variables. So we have this differential equation shown here, or this expression shown here. And we have to separate the variables to solve, given this boundary condition of y of 0 is equal to 1. So what that means, whatever our y equation is, when we plug in 0 for x, the y equation results in 1. So when separating variables, you want to separate the variables and keep one of the variables on one side of the equation and the opposite variable on the opposite side of the equation. So right here we have dy dx, the secant of x, and 1 over y. So what I'm going to do is that I'm going to rearrange this such that everything with or involving y is on the left side, and everything with or involving x is on the right side. So I'm just going to take my y and throw it over, and then take my secant of x and throw it over. So when I do that, I have y, then dy dx is equal to 1 over the secant of x. Well, the secant of x is not very nice to play with. So what I'm going to do is I'm just going to rearrange that, because 1 over the secant of x is equal to the cosine of x. So what I have here is y dy dx is equal to cosine of x. Much easier to deal with the cosine. So then I'm going to split my dy dx, take dx to the right, leave dy on the left. So what I have here is, I'm just going to go down here. I have y dy is equal to the cosine of x dx. So now that I have everything separated into like terms on one side and then the opposite term on the opposite side, what I'm going to do now is I am going to integrate each side of the equation here. So by integrating each side of the equation, looking at the y first, when we integrate y, we end up with 1/2 y squared. And that is equal to, whenever you integrate cosine of x, you get a positive sine of x. And once you integrate, remember, you're always going to get a constant value. Technically, you get a constant for both sides, but since a constant is just some random number associated with this expression, you can just put all of that on one side of the equation. So we're just going to leave our constant of integration on the right side involving x. So the next step would be to get y by itself so that you have an equation that states y is equal to something in forms of x. So taking 1/2 over, so multiplying everything by 2, and then taking the square root of everything, we get y by itself in this form. So the equation of y is equal to the square root of 2 times the sine of x plus our constant. So this is where you're going to use the boundary condition. So once you get y in terms of x in a regular standard equation, then you can use your boundary terms to solve for the constant. Now, if you weren't given any boundary conditions, you would just leave this as your answer. But since you have boundary conditions, you can solve for whatever this constant is. So let's do that. So as I stated earlier, whenever you see this expression like this, what that means is that the y equation, when you plug in x as 0, this y equation results in the value of 1. So when you plug in this, you would have 1 for your y is equal to the square root of 2 sine of 0 for x plus the constant. Well, this one's quite simplistic because the sine of 0 is 0. So this entire thing drops out, and we're left with 1 equals the square root of c. Well, that means that we have 1 squared is equal to c, thus c is equal to 1. So our equation for our expression solving for y is equal to the square root of 2 sine of x plus 1. And that is our answer for this differential equation. Now, since we have boundary conditions, we solve for C, and then we can check it. It's always good to just make sure that you check it. So the way you check differential equations is that you just take your y equation and boop, pop it back in here, and then make sure that it equals what it has to on the right side. So let's go ahead and do that. So when we fill everything in, so we have secant of x, if I can write properly, dy dx. So all that means is that you're taking the derivative with respect to x of the y equation, which is square root of 2 sine of x plus 1. All that has to be equal to 1 over your y, which y is equal to the square root of 2 sine of x plus 1. Now, typically with these types of separation of variable problems, the checking method is longer than the actual solution method. So this is what we're working with right here. We have to make this left side of this equation equal to the right side. So let's go ahead and change this into 2 sine of x plus 1 to the 1/2 power instead of showing the square root. And since we have it in this form, we can use the chain rule to solve for that derivative with respect to x. And if you're not sure how to use the chain rule, we have videos on the channel going over the chain rule under our calculus titles. So what I'm going to do is I'm going to set u equal to what's inside the brackets there of 2 sine of x plus 1. And then I'm going to set f equal to my u, which is just u to that 1/2 power. So this derivative then becomes df dx, which is equal to df du times du dx. Well, du dx is equal to the derivative with respect to x of the u equation, which is simply 2 sine of x plus 1. And this gives me 2 cosines of x, since the sine of x pops out the positive cosine of x. And whenever you take the derivative of a number 1 or any kind of value with no variable attached to it that you're taking the derivative, it just drops out entirely. So the second portion, which is df du, is simply the derivative with respect to u of the f equation, which is u to 1/2. And this is a very, very simplistic, easy derivative to take. So it's 1/2 u to the minus 1/2. Well, since we know what u is equal to up here, it's 2 sine x plus 1, just go ahead and write it as such. So this is 1 over 2 times the square root of u, which is 1 over 2 times the square root of 2. If it wants to click back over to the writing, get off the eraser, there we go. 2 times the sine of x plus 1, all of that under the square root. So now let's put everything back together with df dx. So it'd be this times that. So going back over here, and we have df dx is equal to df du, which is this portion right here, times 2 cosine of x. So I'm just going to go ahead and do 2 cosines of x all over 2 square root of 2 sine of x plus 1. Well, do some simplifications here. And we get rid of the 2's, and we're just left with cosine of x over the square root of 2 sine of x plus 1. Well, don't forget that we have to multiply by the secant up here. So it's going to take all of this and multiply by the secant. So I'm just going to write the word thus, which basically means, instead of, you're skipping a few little things here, or you don't want to rewrite something. So we're saying secant of x, and it's going to be times the cosine of x all over the square root of 2 sine x plus 1. Well, do you remember what the secant of x is? Well, the secant of x is 1 over cosine of x. Well, cosines of x will cancel. Thus, we are left with 1 over the square root of 2 sine of x plus 1 as our final portion here when we take that full derivative multiplied by the secant of x. Is that what's on the right side of the equation? 1 over square root 2 sine x plus 1? Yes, it is. So since our check worked out, that means that this is our answer for y, and that is our answer for this differential equation. So as I said, with these types of differential equations, sometimes the checking method is longer than the actual solution method. But it's always wise to check your answers because there is a lot of potential room for error and mistakes here. So that's how you would solve this particular problem. I hope this video was helpful. And if you want to see more problems solved this Friday, please check out other videos on our channel as we're trying to upload daily. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because it does help us out. Thank you for watching, and I hope you have a fantastic day.